Okay, thank you. So I'm going to be talking about why I think programming language memory models should preserve load-to-store order. So that means this talk is basically going to be about this shape of program. So this is the classic load buffering type example. It's got two threads, they run in parallel. They both do a load followed by a store to different locations. And throughout this talk, I'm going to use capital letters A and B for shared atomic locations and lowercase letters for just local variables. So supposing A and B are both initially 0, the question is, can this produce 73? And there's an argument that it can, and the argument is, well, the left thread loads a variable from A, happens to get 73, then writes 73 into B, the right thread loads that, and then writes the same 73 back into A, which satisfies the original operation. And this is clearly nonsense and should not be happening. This is the classic out of thin air result. And then the question is, how do we define a memory model to prevent this sort of thing from happening? So the simplest and I think probably oldest answer is just ban anything like this. Just say there shall be no cycles in the reads from and program order relation to the program. This has been proposed many, many times in many, many papers, and even still it is still used in recent work. So I'd like to point out that as well as simplifying this and removing all this out of thin air problems, this is actually a really useful reasoning property. Since we're talking about finite execution graphs, to say something is acyclic is the same as to say that it is well-founded, that there are no infinite paths in it. So saying something is acyclic is giving an induction principle. This is saying you can do induction, and in your inductive argument, you can reason about things that are earlier in this order. So you can reason about stuff that you did earlier in the same thread, that's the PO half, and values that you got from other threads, which is the ORF half. So it's useful to be able to do that kind of reasoning, which is another point in favor of having this axiom as part of your memory model. But major memory models, in particular the C and C++ memory model, do not include this axiom. They actually allow load buffering examples, not necessarily the one that I showed earlier, where I just made up a value out of thin air, but some sort of load buffering examples where load to store order is not preserved. And I'd say that there are basically three reasons why that sort of load buffering is allowed in major memory models. The first one is, well, observing that we maybe don't need to worry so much about it just making up a value, because compilers and hardware don't just make up values out of thin air. But the issues with out of thin air under this view are an issue with specifying the model rather than an issue of real practical concern. The second one is, if you look at the hardware and so on that does these kind of reorderings, they only reorder independent ones. Whenever there's a dependency from the load to the subsequent store, like there was in my initial example where the same value is being copied around, then those don't get reordered, only the independent ones are reordered. And that causes no problems. And the third reason is of course performance, that allowing these reorderings, having a memory model which admits load-to-store reordering improves performance. So in keeping with John's request for polemic rants, I'm going to argue that all of these are false, and that we should actually just adopt the axiom that says, let's not have any of these cycles, and let's just order load to store. I think for the first two, there's plenty of examples along these in the literature. I'll provide some more, but I think they're not especially new. The third, I think, is less widely appreciated, but let's keep going. So first of all, compilers, it's hardware, but mainly compilers, do just cause values to show up out of nowhere sometimes. So here's an example using, I'm cheating slightly, I'm using a non-atomic global A, and we're just doing non-atomic accesses, so this is in fact a data race and even worse than out of thin air, than the normal cycles. But in this, we're going to have two threads, and they're both just going to do a single operation. One of them is going to decrement A, and the other is going to do a bitwise OR, setting its low bit to 1. So if these single operations were truly done as a single atomic read modify write operations, then we would expect the resulting value to be either -1 or 0. So it would be -1 if the decrement happens first, then the bitwise OR does nothing, and it would be 0 if the bitwise OR happens first, and then the decrement undoes it. But of course, the compiler does not actually implement these as atomic read, modify, write instructions. Even though they're written as a single operation in the source code, the compiler will split them into several operations. There will often be a load, then the computation of the new value, then a store. And that introduces another possible outcome. We can find that it can also end up being +1. If they both did the load first, they both saw the initial 0, then the minus minus completed, stored back -1, then the bitwise OR completed and stored back +1. So there's another value that can occur because of how the compiler compiles this. Of course, if you actually take this program and you run it on, say, recent GCC and x86, then you will find that when you run it, the values that the program produces are, in fact, -1, 0, +1, and -255. So this is not a value that you really expect. It doesn't show up in the program. It arises from GCC noticing facts about how many bits operations will affect and doing optimisations along those lines. But the general principle I'd like to point out here is, speaking as a compiler developer, do not trust compiler developers. They will do something as weird as they are permitted to do. So anything that says out of thin air behaviors or this sort of behaviors are just a specification concern and no real compiler will do anything that crazy. This is not a trustworthy thing to do. We should really really nail down exactly what the compilers are allowed to do here. So for the second of those points was about the idea that load buffering only happens with dependent operations, and that when there's a dependency, then the load buffering won't occur. So the trickiness of exactly what a dependency is well known. There's many cases of compilers optimizing away fake dependencies, but here I'm going to talk about a dependency that is, at least to me at least, looks real. So here's an example. This is another classic out of thin air example. The question is, can P be null here? So on the left-hand side, P is loaded from A, and if P is not null, we store null to B. On the right-hand side, we load from B and copy that to A. So here, there's the same pattern of both sides doing a load and then a store. And in both cases, the resulting store is dependent on the load. On the right-hand side, there's a data dependency. It's the same value being passed through. On the left-hand side, there's a control dependency. It's the store only happens if the left-hand side occurs. So because of this dependency on both sides, because the value really matters, then the out-of-thin-air behavior can't occur. So the load buffering is not going to happen. So therefore, P will not be null. So we can, because basically the only place the null can come from is that store to B. And that store to B only happens if P is null. Sorry, the store does not occur if P is null. So we know that P is not going to be null. When we know that a pointer is not null, it's safe to dereference it. So let's modify this program and return the value of P. P is not null, so we know that we can look at it. Now, this is a different program. In this program, P might be null. Because this line, the return star P, that's undefined behavior for P to be null. Therefore, the compiler can assume that, for instance, the store of null to B always occurs, because there are two cases. Either P is not null, and the store is in the program, or P is null and behavior is undefined, it can do what it wants, including store null to B. So seeing this operation, the compiler is now allowed to delete the P not equal to null check and reorder the store, moving it earlier before the load, because it is now not dependent on the load anymore, and now P can be null and this program can crash. So I'd like to just look again at the argument in the no case. The argument there was about where might the null come from. It says null only arises from the store to B. So where could the null come from? Well, it could come from the initial value, which wasn't null. It could come from the right-hand side, but that would have had to come from somewhere else. Or the only place it could arise is this initial store to null. That's an inductive argument. I was doing induction there. I was referring to the inductive case being, oh, it came from some other thread that must have gotten it from somewhere, and the base case being where the null came from. That's a use of the induction principle that we would really like to have, but we can't have unless we assume that there are no cycles in program order and reads from. So that no is just not a valid argument in the C++ memory model, and this program is allowed to crash. So that's the second of the three reasons that I think have justified allowing these cycles. The third one is performance. So now I'm going to argue that allowing load buffering makes performance worse, at least in some cases. So here's a fragment of C. This fragment of C should really return 0. There are no data races here. No other thread ever accesses these memory locations. We set star q equal to OR, and then we return star q minus OR. So at this point, the two values subtracted are going to be equal. That should return 0. So let's look at the rest of the program. Let's look at some context here. R is a local variable. P is a parameter to the function. Q is some pointer that we got back from calling foo, which is some unknown outside function that we called, and we gave it the address of R. Then we do this sequence of operations. We assign 2 to R, 1 to P, or to Q, and then do that in subtraction. So the current release version of Clang compiles the last block of code, the last 4 instructions there, to the following sequence of ARM64 assembly. It puts 2 into this W8 register, 1 into W9. So then W8 is stored to X2928. That's the address of the OR local variable on the stack. Then it stores 1 into P. And then, very interestingly, there's this third from the last instruction, the store of W8 to X0. That's storing into Q. It's the third operation here. But the value that it's storing in there is 2. And putting 2 in there means Clang was doing something quite complicated. Clang noticed that P and OR cannot possibly alias, that they must be different locations. In particular, the write of 1 into P cannot have overwritten the write of 2 into Q into OR. On the basis that, well, P is something that you got as a parameter, or is on your stack, or wasn't even defined by the time you got P, so it must be this new fresh location. If, for some reason, or P was equal to the address of OR, and these things did overwrite, then this code would return the wrong answer. This code is doing a subtract of, it does at the end 2 minus the contents of OR. If the contents of OR are in fact 1 at this point, then it would return a non-zero value, which it really shouldn't be able to do. So this code is correct only on the assumption that star P and OR do not alias. But of course, they might alias because of load buffering. So if the contents of foo are to do a relaxed store of the value that it got, and when we call the function go, the thing that we pass to it is the contents of this global atomic variable A, and we've another thread that does a load and a store, then we have this same pattern. We have this thread doing the thread on the left doing the go function has a load of A, and later an independent store of B. That independent store can be moved before the load. The other thread can load that, return the same value, and then that can satisfy the original load. And this is allowed. This is a reordering of independent values.
But isn't that a race that you mean? Like that's non-atomic locations, but compiler does that only for non-atomic, and your example has a race on non-atomic locations.
Sorry, no, my example is no race to non-atomic locations. There's only one thread. Sorry, the other thread is only doing atomic accesses. Sorry, when I say load relax and store relax here, I mean atomic, like atomic load explicit memory order relaxed.
So you mean this is compiler, then you have a miscompilation for these programs, which is a well-defined program, or maybe I missed.
No.
Yeah, what's the type of A and B?
A and B are atomic int stars. They're atomic variables holding int pointers.
Thank you.
So the point of this example is that it means that because of load buffering, fresh locations are not necessarily fresh. If you define a new variable on your stack, its address is not necessarily distinct from other pointers that you have lying around. A newly defined, or for instance, the return value of malloc. The return value of malloc is not known to be different from other pointers that you have, because the return value of malloc could later be stored into an relaxed atomic variable. That could be copied to a different relaxed atomic variable. That could be loaded, and that load could have been in your program earlier than the call.
Actually, that's exactly the... Yeah. So, I mean, we worked on it. We have a solution for this. I mean, we encountered the same problem. So we developed the weak memory model for non-atomics, and we found that the flow-sensitive escape analysis is wrong. So we think that's compiler bugs. So that's because of compiler bugs, and we discussed with LLVM and GCC, and they think it's a compiler bugs, and so they will fix it. So I think that's not problem with the modeling. Somehow they did something wrong with the escape analysis. So somehow, yeah, I think it's related to escape analysis.
Yeah, I think that sounds like the same thing. So here I mean, I'm thinking of it in terms of aliasing, but it's essentially the same problem of at the start of this function, could or have already escaped? Could the address of or be the same as the value of p?
Not every load buffering is a problem. Only some load buffering is a problem, and compiler shouldn't do that load buffering. And then compiler writers, that's their mistakes.
Right, but I'd like to point out the load buffering is not visible in the source code of this problem. What caused the problem here is a compiler transformation on completely sequential code. The code on the left there contains no uses of atomics. They happen to be used before this function was called and in the body.
But that's compiler bugs anyway. Even if it's completely sequential, they should be careful about escape analysis. It's their bugs. So that's my viewpoint.
So I agree that this is a compiler bug with respect to the C++ memory model, which
right, and
permits
that's fixable,
this sort of
and then that's the correct. I mean, that's a fixable bugs.
I mean, yes. I mean, most bugs are fixable if you do some work.
I'm saying is a load of it's not essential problem with the load of buffering. Just compiler developers made mistake, and load of buffering is okay. Other cases.
Right. So the cases which is. You can't tell from looking at the program that this is one of the cases where it's not okay. This is just a sequential optimization that can never be done because of the possibility of load buffering.
No, we have a sequential model, and where every sound optimization in this sequential model is also sound in the fully weak memory model. We have Coq proof.
Yes.
So in our sequential memory model, sequential execution model, there is some gadget that disallow the kind of load of buffering, but all the other load of bufferings are sound. And we have formal proof that all the other load of buffering is sound in the weak memory model.
Right, but
in the, okay. So, okay, sorry.
Right, so I think we're basically saying the same thing, but disagreeing about whether it should happen, which is that soundly allowing load buffering means inhibiting optimizations of sequential code, specifically these kind of flow-sensitive escape analysis ones. And I am arguing that that's bad, and languages, I mean, maybe it's too late for C++, but languages like, for instance, Rust, that's still agonizing over exactly how its model should be, should not allow load buffering because you get these standard optimizations still work for sequential code. And I also argue that the cost of preventing load buffering for relaxed atomics is really very small. The only bit of published actual numbers I've seen from this is a paper by Dembski in 2018, which added fake dependencies to prevent these reorderings between loads and stores of relaxed atomics. And they did this, so this of course has no cost for sequential code, but for concurrent code that took some data structure benchmarks, did nothing but the concurrent data structures, which is maybe an unrealistic amount of relaxed operations to happen, and found that the average cost was they got very slightly faster when they inserted these extra operations, which means it's just completely in the noise. There was one benchmark that got 6.3% slower, which is again in the noise, I would say. I mean, if you think this is not in the noise, I'd point out the work of like stabilizer and so on, which show that you get plus and minus 30% swings in benchmarks when you change the length of the username of the person running the benchmark. But I mean, if you have a data set that's averaging out to below 0, some of them are above a few percent and some of them are below.
if your load and store are separated by multiple function calls, how do you introduce a fake dependency through the ABI of multiple function calls? Like?
Oh, right. So there's a few techniques. There's a couple of them listed in that paper. So the simplest one is to have a branch after the load, because everything after the branch has a control dependency. Yeah. There are other few slightly trickier ones, but it's doable. Oh. Right, and then if we don't have load buffering, then we get to keep the sequential optimisations. We get to reason inductively on values, and we get to keep programming logics. Like the Rust belt relax logic, for instance, works on Rust, but assumes this axiom. So if we have any time left, I'll take some questions, but also I think we should just have this axiom. It's great.
Thank you, Stephen. So, one last question, and then we better go to lunch.
Not a question, but a more observation. My understanding is that a few percent slowdown isn't acceptable to implementers who use relaxed atomics. They want the atomicity, they don't care about the order. And when they're running this on a load of machines, that's going to slow down quite observably. This is something that I think Paul mentioned to me in an email. But the question is, in practice, would this be accepted, even if in theory we keep all these nice theories?
So, these numbers. So, we need to do more benchmark to get more believable numbers, or like more numbers. If you're talking about over a large collection of machines, and that's a statement about the average, not a statement about one particular benchmark. The one paper that I have that actually measures this shows some getting slower, some getting faster, and averaging out to a wash. So it's not clear that this would be multiples of percent or even a single percent move in either direction.
Cool. Great. Let's go for lunch. Back at 2. Lunch is in